Samai, thank you for the kind introduction. This is my bio. Okay. Today, good afternoon, everyone. In this talk, I will, the title of my talk is Leveraging Machine Learning Techniques to Enhance Traditional EDA workflows. So it means briefly, it is about the ML or AI or EDA, ML-based EDA. It works. This is my university poster. It's a real photo. It's very clean, and Pohang is located in. Sorry. It's working. Let me use this. Pohang is located in southeast part of Korea here, and this is my lab. Okay. Nowadays, we spend more than $500 million to design a chip. As you know, this design crisis is due to the huge increase of TAT, turnaround time, which comes from too many design rules and transistors. With this background, AI and ML can be a breakthrough to enhance the efficiency of traditional EDA workflows, especially in two ways. AI ML can predict design quality. Thank you. And from the design space. And also the AI ML can improve QOR, the quality of results, with learning-based optimization. This was a kind of famous research from Google, right? Google used a reinforcement learning to place the macro cell. As shown in this picture, they placed the macro cell, and after that, they placed a standard cell with the traditional way and updated the reward function, which is composed of the wire length, the metal wire length, and congestion. And after that, they could. Okay, thank you. So this is not the real picture, but left one is kind of a human make this kind of macro placement. These macros are SRAM or analog blocks, and AI can make this kind of results. So it's we think that this is much better than this one because they are because we can place a standard cell in these white spaces, but AI shows the different results. But this right one is better than the left one. So still there are many questions about the AI or ML-based the EDA, if it is so effective or helpful, but the traditional flows requires exhaustive runs and large design space exploration, and in this case we can use AI or ML for the traditional EDA workflows to improve both the TAT and QOR. So we can categorize this help in three categories. The one is prediction, another one is optimization, and the last one is generation. So our group is working on these three categories, and this is our recently published AI EDA works in 2 years ago. If you see the publications, we applied ML and ML techniques for each design flows, from the custom design, TTCO, and place and route and sign off. So we published 10 papers in 2023 and published also 10 papers in 2024. And this year we already published 5 papers, and yeah, we need to publish 5 more papers this year. In Taiwan there are many EDA professors, right? More than 20, maybe. Yeah, but Korea, we don't have many EDA professors. So it will be, in the physical design, it will be less than 5. So that is why I'm working all of the range of the physical design part. The first topic is early stage prediction. So in the place and route, the most time consuming part is the CT after the CTS and post route. So placement takes just less than one day, just a few hours, but CTS and routing takes a few days. So if there is the results, after the routing results is not good, then we should iterate again and again. So it takes a long time, right? So we want to minimize this iteration, or we want to make the short loop using the ML. If we can predict the results of the after the placement, if we can predict the results, then we can make the loop much shorter than the previous case, and we can reduce the iterations and we can reduce the design time. But in this scenario, we need to several things to think about. The first one, we need to improve the prediction quality. We need to have enough training data, right? And we should use better model. And also, if we predict the result, then we need to select appropriate optimization method based on the prediction. So we addressed these 3 items in our publications. The first publication is about the artificial lineage generator. So in the morning, the Professor Rin mentioned about that the data is very important, right? And we don't have enough data for the design, of course. So our group developed this lineage generator. It can generate based on some topological characteristics of the design. We extract such characteristics from the real design, and we can regenerate the different designs. So with this artificial lineage generator, we could use the 320 different lineages, and also we could use the design options 180. So we made 20,000 place and route results for the training. So this 320 data is a well-balanced data. It means that if you see that this TSNE graph is the 2-dimensional trajectory of the design, the characteristics, the red one is the real data, but blue one is artificial data. So artificial data can cover more design space, and it is much more helpful for the training. Also, our generator can be used in the different pattern generation, and Samsung Office team used this lineage generator, and they could have 30% more metal patterns. So in their OPC work, the Professor Rin's work, right, such kind of that, they wanted such OPC data before the real design, because if they study the new technology load, they want to study the OPC the pattern work, but they don't have the design. That was the problem. So we could provide some not real, but artificial design to them. Another work for the early stage prediction is to improve the quality of the model. The one problem of the data is that we use the layout data, and they have some hotspots, DRV hotspots, but it's a very imbalanced data. For the data, we divide it with a small portion of each part, and most of portion don't have the DRV violations. Only some small part of the dam has the DRV violation, so it's a very imbalanced data, and it is not easy to make the training results. So in this case, we use the two-step, the hierarchical, the training and inference, that is the classification and regression. And last one, after the prediction, if we know that where is the DRV hotspot, then we should modify the placement, right? But we don't know why there is the DRV violations. Some DRV violations causes from the metal, but another one is because of the placement issue. So in that case, we can use explainable AI. The explainable AI can explain why there is the DRV hotspot, and it is related that there should be some the square metrics. Yeah, let me see. And based on this square metric, we can choose appropriate optimization options. So with this technique, we could achieve the more than 70% DRV reduction. Okay, and the second topic is the design optimization, especially on the timing. In the EDA, the timing optimization is very important, right? And we are optimize the circuit timing using the buffer insertion and case sizing and VT swap. But in the traditional algorithm or traditional heuristic, we apply the technique not simultaneously, sequentially. So that is some iteration of buffer insertion and iterations of the case sizing and iteration of VT swap. So then this sequential application of the method can cause the suboptimal result. So we changed this approach to the simultaneous application using the reinforcement running. Also, previously we used the cost function that was a weighted sum cost function between the power and timing. We want to reduce the timing violation. Also, we want to reduce the power. That is the trade-off, right? However, if we use the multi-agent, then we can optimize the timing and power together. So in our approach, one agent improve the power, reduce power consumption, and another agent want to improve the timing. So each agent has a policy and value network, and they communicate with this total environment based on the real commercial tool. This is we receive the data, the circuit data based on the graph, and we use the graph convolutional network. And after that, we choose based on each agent determine which policy is the best, and based on that policy, we change the circuit. We upsize or downsize, or VT swap, or buffer insertion. And after that, we could improve the results. If you see the palette frontier, graph, the x-axis is power consumption and y-axis is normalized. The TNS is the timing violation part. And this rower is better, and our approach is much better than the previous other works. We can use also the ML for the timing optimization in the dummy pattern insertion. Dummy pattern is required for the CMP, and we generated dummy pattern based on the generative model Kang. It's very similar to the Professor Rin's work, and we used this UNet for the generation, but we also used this the discriminator. This is a GAN structure. But the problem is that using this GAN, we can generate dummy pattern, but however, the generated one is a kind of image. So there is the blood image, and so this metal pattern should keep the design rule, and so we have to add some post-processing. So it takes much time. So our next work was we used the reinforcement running. The idea is the first we add excessive field, and after that we analyze the timing critical path, and on the timing critical path we remove the field much more than the other part. So when we remove the field, the free inserted field, we use the reinforcement, we use the policy network, and we use the reinforcement running here. So I don't have not enough time, right? So my last topic is the HDL generation using large language model. Nowadays, this topic is very hot, and other groups are working on this. Yes, LLM nowadays we can use LLM for the HDL generation, right? Like the C and Python. LLM LLMs are very good for the C and Python, but still HDL they are not good. This is this slide came from my VLSI design class. It's the TOM project. It's for the designing convolution block. The convolution, very simple convolution block, but there is the interface with the SRAM, and also, it is not difficult, but we try to make the solution with the ChatGPT. So we provided system prompt and the manually written HDL description and module description and some images from the LAM access and waveform also. But the generated Verilog code was there was some syntax error because this style was a C or C++ syntax style, and also after some iterations to solve this issue, and there was also the test bench simulation failed. So still, it is good for the digital circuit designer, right? Still, ChatGPT doesn't make a good solution for the Verilog HDL. But however, after, I'm not sure, after 3 or 4 years later, ChatGPT can design the Verilog better than the human. I'm not sure. Anyway, to improve this quality of the LLMs for the Verilog HDL, there are two approaches. One approach is prompt engineering, and another approach is fine-tuning. In the prompt engineering, we we optimize the prompt to get the desired output. So it can quickly adjust the model's output by modifying the prompt. However, it shows the low accuracy for the information. But fine-tuning, yeah, we can modify the models. The modified model models can be tailored to suit the specific task. For example, the HDL generation. And so this fine-tuned LLM, compared to the baseline LLM, it can generate better HDL with the fine-tuned LLM. However, it needs large data for the training. So this work will be presented in this year's date, and the contributions of our work is the first one is the AST, Abstract Syntax Tree-based data augmentation. Using this technique, we could make more payload codes. And another contribution is we also make the output-relevant code masking, because we should prepare the data for supervised running, right? The data pair is one is the description, another one could be the payload code. The problem is we can gather payload code, but we should make descriptions. It is not easy, right? So instead of making the description, we masked some code. Also, we use the reinforcement learning with tool feedbacks. And this is overflow, and there is the AST-based data augmentation and code masking that is related with the training data generation of training data set. And for the fine-tuning, with this generated data set, we make the supervised running, supervised fine-tuning, and also we added the reinforcement learning with tool feedback. The tool feedback means the feedback from the real characters. Yeah. Using the AST, we can convert the original code, HDL code, to AST, and we can modify this AST, the tree graph, to the augmented AST, and from this augmented AST, we can convert this one to the value code. So this slide shows more details. This is original AST, and this is some modification in the operators, and we can insert some node or we can delete some node. So this AST-based augmentation cannot generate very different value from the original one, but it can make some similar but different one. So it is helpful for the supervised running. Also in the code masking, so it's we prepare the data pair. This is original HDL code, and it's the masked data. So in the training, we provide this masked data, and the solution is this one. So we can use these pairs for the training of fine-tuning of the LLMs. The last one, reinforcement learning with tool feedback. This is we added during the fine-tuning of the LLMs, we added this tool feedback loop inside of the training flow, and with the EDA tool, we made syntax checks. This is a lint check, and also we made a formality check. This result is forwarded to the based on this check, we can calculate the reward, and this reward value goes to the feedback as the reinforcement learning. We made these experiments based on our baseline model was DeepSeek, and we used NVIDIA A6000 GPUs, and yeah, this is environment. And the result shows that if we don't use just the real data, and we compare with we compared with only the real data and real data plus augmented data results. And also, we compared with other previous work, GPT-4, and our result was better than the GPT-4, but the size of the LLM model is very huge. It shows it's a very huge. There are very huge difference, right? Okay, this is the summary of my talk. So ML can be used the EDA, but there are still many limitations and hurdles, and we applied ML to these three categories: the prediction and optimization and generation. In the prediction, with the early stage prediction, we can reduce the tool iteration. However, there are still the generalization issue for unseen data. If we train the model with some data or some technology node, then that model cannot be used to the totally different unseen data or the different technology node, right? So that is the big problem. In the optimization, usually we are using the reinforcement learning, but the limitation of reinforcement learning is the reproducibility issues, right? And also in the generation, if we can use the LLMs for the code generation, or then the productivity will be increased, right? But still there are the many issues, correctness and verification challenges. Okay, this is end of my talk, and thank you very much for your attention.
Thank you so much, Professor Kang. So, do we have any questions from the audience? Yes, please.
For the adaptability optimization work in the ICCAT 23, how to make sure the label are comprehensive? So what's about the cost for the label? Because I think the present ZAO actually have a wide range of patterns. So how to make sure the label data are comprehensive enough?
You mean the ICCAT 23,
the optimization work?
Oh, reliability optimization work. So, and sorry, I didn't understand the label.
So I mean that because the routing patterns actually are many kinds of routing patterns. So how to make sure you have enough data to do to supervise your learning?
Okay, yeah. It's a good question, and thank you for the question. Right. So, of course, there are so many patterns, the routing patterns, but for the supervised learning, we don't use the patterns. We use the picture from the layout, the congestion data and the timing data, and we divided the layout with a small grid. Inside of the grid, there are we use the data. There are how many standard cells are there, and how about the utilization of the. So such data is.
Some tool to find such kind of design tool violation patterns.
Right. Yeah, that's right.
Okay.
Yeah.
Thank you.
Curious about how far away the LLM can help the HTL engineer coding. Real life.
Yeah, The first I think, yeah,
Which level you can do that, and how far you can go in future?
the answer is, yeah, it's very difficult as a question actually. But the problem is that in the website there are so many source code for the C++ and Python, right? However, we don't have enough. We cannot find enough data for the good data for the fellow code. So that is one problem, and another. But the direction is there. Now, the synopsis is making some framework like the Copilot. So if designer write the code, value code, then synopsis can provide the description, and just if we just make the command, then the Copilot-like framework can generate entire code automatically. But even though the designer should check if that is correct or not. So that is the current state. But future state, I think it should be changed, right? Yeah. When LLM can be more smarter than human, I'm not sure.
A following question maybe, is it possible that LLM or AI could replace HDL engineers someday? Yeah, are we creating our replacement?
Yeah, that will not be the replacement. I think engineer will be required for other works, right? So if AI generate the design results, then we should determine if the design is good or not, or such kind of things. Yeah.
Yes.
Yes, I actually offer HDL lectures for the last semester.
Oh, I see.
Online exam, okay. So it's open book. Students can reference everything they want. So students simply ask me whether they can use the ChatGPT. I said, fine. Okay, ChatGPT can understand my problem description and then write the correct code.
Sure.
Then that's okay. Anyway, that's the advance of the. We have to take advantage of the advance of the tools.
Of course.
Yeah, I think back to the question. I think in one of your work, okay, you mentioned that you can actually employ multiple agents.
Okay.
Okay, in your reinforcement learning process, so like achieve the multiple goals of.
Oh, right.
So my question is that how do you coordinate? Okay, these different agents. Maybe they have different goals.
That's
One
right.
may be the area, the other may be the speed. Okay, these two goals are actually complement to each other. So do you need to kind of prioritize the agents, or at least put some weight okay, in terms of the reward function, something like that, so that you can come out with the satisfactory results?
Oh, yeah, it's very good question. And for the multi-agent optimization, each agent compete each other, right? Yeah, and in that case, we don't put any priority of them. The reason is that previously we modeled the reward function using the weight parameter, right? If there is the multiple objective, right? But in this case, if then we cannot, in that case we couldn't find which parameter, which weight was the best for the final results. It was very difficult. So we just used multi-agent to compete each other. But their results, they shows the very different results. If you see my previous slide. Sorry. So they provide very different results based on reinforcement learning has the kind of random move, and they provide some different solutions. So, but we can iterate this reinforcement learning based solution. We can iterate them, and we can select some of them. So, I mean, yeah, I'm not sure this is enough answer, but yeah.
Okay. I think with the time limit, let's thank our speaker again.
So thank you very much.
Thank you so much.